When an enterprise application attempts to write a record into a relational database that already exists, the incoming data collides with a unique constraint. The database engine rejects the insert and fires back an error. If you are running MySQL, the database throws a proprietary error code, 1062. A common initial response is to catch the raw SQL exception and write a manual check for that specific 1062 code, routing the application logic accordingly. The application will run cleanly until the infrastructure team migrates the backend to SQL Server. SQL Server identifies the exact same constraint violation using error code 2601. The check fails and the application crashes. Relying on vendor-specific error codes tightly couples your business logic to a single database vendor, violating clean architectural boundaries. The Spring framework addresses this by providing a generalized data access abstraction layer. This layer sits between your service logic and the database driver. Its design purpose is to intercept raw, proprietary vendor exceptions and translate them into a unified, predictable hierarchy of Spring-specific exceptions. However, this automated translation often works flawlessly for some data access tools, while appearing to fail silently for others. We are going to map exactly how Spring executes exception translation across two distinct architectural pathways. Understanding these two mechanics allows you to write resilient enterprise systems that decouple your business logic from the infrastructure layer. The foundation of Spring's data layer is a unified exception tree. The root node of this tree is DataAccessException. This hierarchy is composed of unchecked exceptions. By converting checked database exceptions into unchecked ones, Spring eliminates the need for boilerplate try-catch blocks across every method in your application. The tree structure separates unrecoverable systemic failures, like a dropped network connection, from specific recoverable data errors, such as a duplicate key exception. Restricting the service layer to interact solely with these standardized Spring exceptions ensures your business logic remains decoupled from the underlying database technology. The mechanical question is how a raw, proprietary SQL error navigates to its precise location on this tree. The underlying translation mechanism depends entirely on whether the application uses low-level JDBC or high-level object relational mapping. The first pathway involves executing queries directly using Spring's JdbcTemplate. JdbcTemplate is a self-contained unit. It manages resource creation, statement execution, and error handling within its own internal workflow. When a database error occurs, the template intercepts the raw exception and invokes a specialized component, the SQLErrorCodeSQLTranslator. The translator executes a two-step process. First, it queries the active database metadata to identify the specific database product name. Second, it cross-references the proprietary vendor error code with an internal Spring configuration file named SQLErrorCodes.xml. This file maps the raw vendor code directly to the appropriate data exception access subclass we saw on the tree. This entire pipeline operates automatically. It requires no external configuration or specific annotations from the developer. For JDBC, exception translation is natively baked into the execution flow, isolating the developer from vendor specifics at the point of query execution. This internal pipeline works for JDBC, but object relational mapping frameworks like Hibernate or JPA present a structural conflict. ORMs possess their own proprietary native exception hierarchies. These are distinct from raw SQL exceptions and entirely separate from Spring's exception tree. Spring cannot force a third-party library to throw Spring-specific exceptions natively from within its own compiled codebase. Spring requires an external mechanism to intercept and translate these ORM-specific errors before they reach the service layer. Spring solves this dilemma using aspect-oriented programming. Applying the @repository annotation to a data access class changes the underlying structure of the bean within the Spring context. The @repository stereotype triggers the persistence exception translation postprocessor during application startup. This postprocessor wraps the original data access object within a proxy layer, creating a structural checkpoint around the bean. If the ORM throws a native exception during a standard database operation, that exception attempts to travel upward towards the service layer, but before it can exit the bean, the proxy intercepts it at the boundary. The proxy evaluates the intercepted ORM exception and converts it into the standard Spring DataAccessException equivalent. Identical logic behaves differently depending on the tool. ORMs depend on this external AOP proxy for translation, whereas JdbcTemplate performs the same task internally. If the @repository annotation is missing, the proxy is never built. Native ORM exceptions bypass the translation layer and reach the business logic. The @repository annotation acts as a functional switch that activates external AOP exception translation. Applying this framework knowledge allows you to correct flawed architectural patterns at the application level. A common developer workaround for avoiding database errors is the check-then-act pattern, querying the database with a find-by method to verify a record doesn't exist before attempting to save it. This pattern breaks down in distributed, multi-instance systems. If your service is running multiple instances under high concurrency, two separate servers can perform the recheck at the exact same millisecond. Both receive a not found response, and both attempt to persist the object. They collide. The database constraint violation will bypass the preliminary recheck, forcing your application to handle the exception you tried to avoid. Application-level rechecks are unreliable for enforcing data integrity under concurrent load. JdbcTemplate processes exception translations internally, while high-level ORMs require external AOP proxies activated by the @repository annotation. Mastering this dual architecture ensures that your service layer only ever processes standardized Spring exceptions, regardless of the underlying tool. This allows you to rely on the database engine, the system designed for concurrency, to enforce strict uniqueness and data constraints. Fully utilizing Spring's automated translation layer enables a robust, decoupled architecture that cleanly manages unavoidable database collisions without compromising your business logic.